Okay, thank you for reminding. Yeah. So under tectosilicates, which is the robust type of silicate group, we have silica group, under which you have quartz, tridymite, cristobalite, opal, and also chert, family members. Okay, so they are purely Sio2, and rarely some trace metals or trace ions can be substituted, but the structure is not stable under such conditions. Very much stable. It's not very much stable under such conditions, right? So this opal might contain some water molecules, but which are not absorbed into that. We call it adsorbed, AD, right? ADSORPD, as adsorbed. So easily that water molecule can be removed. Then we have the other group, that is Feldspar group, and these feldspars are divided into two groups broadly. K feldspars and Plagioclase feldspars. So potassium feldspars and Plagioclase feldspars, they distinctly differ their compositions in terms of solid solution. So I think by now you understand what is solid solution. We have a separate solid solution. I have some lecture materials, so I will upload that also for your additional reading. Okay, so solid solution, under solid state condition, diffusion controlled ionic exchange inside a molecule, right? That is solid solution. So no liquid or nothing melting or anything is involved there. Under solid state condition, movement of ions within a molecule, which is mainly temperature controlled. Okay, so potassium feldspar and Plagioclase feldspar, two families are there. So we will see their compositions later on. And under K feldspars, you have microcline, one group, one type, one variety. Then autoclave, and another one is called sanidine. So their basic composition is this one. So once you see this composition, right, it's very hard that to distinguish between them, whether it is microcline or autoclave, just by looking at the formula, right? Because the formula is common. But there are some other optical features. That means you have to see that under optical microscope, metrological microscope, polarizing microscope. Then you will realize whether this is an autoclave or microcline, right? Some textural feature. I think by now you have already learned about these textures, but once the university is open, you can see some examples, right? Some twinning types, cross-hatch twinning, basically twinning types you can use for distinguishing autoclave and microcline. Microcline is normally cross-hatched. It's like square shaped. Twinning is there. Some pattern is there on the grain itself when you see under the microscope, right? So these three K feldspars are available, and under Plagioclase feldspars, what you have is albite, nanotype compositions basically. So what is albite and nanotype? Albite and nanotype is a solid solution between sodium and potassium, sodium and calcium. Okay, albite is a sodium end member. We call sodium end member. See here, this is the composition of albite, right? The composition of albite is here, and nanotype composition is here, right? So you can see sodium and calcium replace themselves to change their composition. So in between also you have compositions in between albite and nanotype. So based on the concentration of this component, that is alkaline component or alkaline earth component, right? Sodium or potassium, sorry, sodium or calcium, we term it whether it is an nanotype or albite. So if you have more sodium, then it's more towards albite composition, and otherwise it's nanotype composition, right? So they belong to tectosilicate group. In addition, you have some other types of groups also, But remember, the silicate group and feldspar group are the dominant type of tectosilicates available, right? So there are different crystal symmetries for each of these minerals, okay, and properties also. Therefore, right. So we have another group that is called Feldspathoid group. So these are very not very common, very rare types, right? But available in igneous rocks, right? In igneous rocks. But the silicate group, the silica group and feldspar group, as you know, is very common. It's available in any type of rocks, right? Not particularly in igneous rocks, but these feldspathoids ones, they are sort of special type. We call sometimes silica poor also, because although silica is there, there is no sufficient amount of silica tetrahedron inside those silicates, although they are silicates. So therefore, we call them silica poor silicates. So some categories are there: lucite, nepheline, sodalite, lazurite, and petalite. Right. So these are rare types of tectosilicates which belong to Feldspathoid group. We call it Feldspathoid group. Right. And then we have another group, that's scapolite series. Scapolite. It's a little bit complicated. The chemistry is a little bit complicated. Right. You see here, it's not as simple as like silica. We have under scapolite series, Mariolite, Meonite, and Anacime. Right, this is a very rare one. I think actually you don't need any. You don't need to remember this chemistry in these rare types of groups, right? But you have to keep in mind that these series are available. Okay, right. And then we have another one that's called zeolite group, right? Zeolite group. Under zeolite group also, you have natrolite, chabazite, hewlandite, stilbite, right? Those are the sub members under that group. But you have to remember all these group names, right? Definitely you have to remember these group names. And for feldspars and silica, you have to know all these subgroups as well. Okay, so it's important. And under igneous petrology, you might learn about this group later on, right? In your next year, you will get chance to learn about those things, right? But for this content, you must remember all these subgroups as well under silica group and feldspar group. But apart from that, you have to remember other group types, right? The subvarieties it's better if you can remember, but not essential. So anyway, tectosilicates belong to framework type of silicates. So that is a robust silicate. Please insert your registration number for marking attendance in the chat box. Right? Don't forget that. Okay, right. So we will see in detail about the silica group now, Sio2 group. Okay. So we considered that there are several varieties: quartz, tridymite, cristobalite, and opal, and chert, right? Those are the varieties, and we'll see a little bit details. You have different symmetries, right? For these varieties, different symmetries. You know, the crystal system is different, right? It depends on the formation conditions. Okay, right? Because I said these are different in terms of the physical conditions they form. That means temperature and pressure, right? So especially this coesite, this one, coesite, and Stoichiometry. This is called Stoichiometry. S is silent, although S is there. It's Stoichiometry, not that long, right? Stoichiometry, not Stoichiometry or something, right? Stoichiometry. So this Stoichiometry is a mantle mineral, right? It is found in the Earth's mantle, right? It's under very, very high pressure conditions. When you go very deep into the mantle, you see this quartz is converted into tissueite, right? That's what it's happening. It's a polymorphic change. We call it a polymorphic change. That means no chemical change, but only structural change is there, right? Crystal chemistry is constant. That's what you mean by polymorphs. So if you have a mineral, there is structural changes, but not chemical changes, right? Remember aluminosilicates, sillimanite, kyanite, and lucite, those are polymorphs. Right? So likewise, these quartz have polymorphs, that is tissueite, coesite. And also you have low alpha quartz, high beta quartz, actually basically alpha quartz and beta quartz, right? Depending on the temperature conditions. See this diagram, you can see this diagram. You have the pressure and temperature conditions, and you can see the stability fields, stability regions, right? So low quartz means alpha or beta under low pressure and low temperature regions. But of course, this is not low temperature in this region. It can vary up to high temperature also, right? But basically towards the low pressure side, right? But although this 20 kilobars is not considered as a low pressure when you talk about the Earth's crust, right? But since in this diagram it comes to the low pressure and low temperature side only, we refer it as low temperature and low pressure. But it's a sort of what is a relative terminology, right? In a real environment, it's not the real low temperature or low pressure ones. But of course, for this high quartz, tridymite and cristobalite, we call it high quartz due to their presence under high temperature conditions, right? Very high temperature conditions, because you know above 500, above 800, like here, right? Temperatures are considered as high temperature, right? So you have tridymite, cristobalite. Those belong to high quartz, and low quartz means other types of quartz, I mean silica, normal silica, which is found in this region. And when it goes to very high pressure regions, like above 20 kilobar, right? Physically, we consider as high pressure conditions in the real environment, in the real crustal environment. And there, this low quartz, normal silica, converts into coesite. Okay, they can convert into coesite when you increase the pressure. So increasing the pressure means, for example, a subduction zone, right? So from low pressure regions, the rocks are going down, subducting into high pressure regions. So there you have what you call high pressure varieties of quartz, that is coesite, right? Coesite is formed in such rocks, and also there's a volume change also forming. It's a very typical feature for coesite formation. That means increasing of volume is taking place because there is a structural change taking place in coesite, because you can see here it changes to monoclinic system. Okay, so that's a different thing. So this volume change is indicated in the rock itself. When you see the thin section, even rock thin section under the microscope, you will see very, very characteristic feature. Here, suppose this is the coesite grain. So around that grain, around this grain, what you will see is just some arbitrary cracks, some cracks form. Why these cracks are formed? This is the grain, this is the mineral, but outside the mineral, you see maybe another mineral is here. That mineral is get cracked because of this coesite formation. So what happens in the coesite formation? I said there will be a volume increase. So accommodate the volume, it's like expansion line, right? So then gets some cracks. That is happening. So this is a very characteristic feature for coesite, and you can use that feature alone to identify coesite from quartz, right? Because optically it's same. You can never distinguish quartz and coesite under thin section, even under chemistry. I mean, if you do analysis, chemical analysis, you can't distinguish, because quartz is SiO2, coesite is also SiO2. You are getting the same composition. So then how can you distinguish, right? Only thing is you have to go for XRD or Raman spectrometric analysis. Then you will see the structural differences in such analysis. Okay. Otherwise, you can use this simple textural differences also to identify coesite. Okay. So this is a different variety of quartz under high temperature conditions. And tissue-white is here. You can see it's occurring above 75 kilobars. Above 75 kilobars means very, very deep in the earth. It's beyond the Earth's crust. That means it goes to the mantle level, right? So in the mantle, you find this high pressure quartz variety, which is tissue-white. But basically, in optical sense, all these varieties will look like this, right? Apparently look like this, but you don't see this crystal shape. This is available only for the quartz, okay? And this type of crystal phases only you can see in quartz, because the crystal structure, when it changes, for example, coesite, it's monoclinic, so it's a different structure. It's going to give you different structural features, because you see some are hexagonal, because quartz is hexagonal, right? And monoclinic, orthorhombic, right? Tetragonal, isometric, even isometric, cristobalite, high beta cristobalite, isometric, right? Isometric means it's cubic, right? Optically, you will see nothing under CPA when you cross the polarizers, cross-polar line, right? So likewise, you will have different structures in this tectosilicate group. So this is an important type of group because silica is the dominant mineral phase in the earth crust, and also it is the simplest form, right? SiO2, just SiO2. It's very simple chemistry. Okay. Did you understand? Any question? Do you have any question? So if you have any question, please ask now. Okay, so we will go ahead then. I don't see any question. Don't forget to put your registration number in the chat box. Okay, and also just to remind, I have uploaded an assignment, so you have to go through that and submit on or before 31st October. I will put some additional notes also for your reference, so you can go through them as well. Okay. Right, then we will go to the next group, that is Feldspar group, right? Under tectosilicate, we just looked at the silica group, and now we are going to Feldspar group. Okay. Right, where is the Feldspar group? Okay, right. Now, as you can see here, there is a compositional triangle for Feldspar group as well. So what is the special feature in this compositional triangle? So I already mentioned that there are two varieties of feldspars, mainly two varieties, that is microcline and autoclave, right? This is the commonest form of feldspar, right? Sanidine is not very common in many rocks. It's found in igneous rocks only, okay? But I said you have K feldspar and Plagioclase feldspar. Those are the main two groups. Okay, under K feldspar you have microcline and autoclase mainly, and under Plagioclase feldspar you have albite and nanotype, as I said. Okay, we'll see now how this composition change. So this is termed as alkali feldspar. So what is alkali feldspar? Alkali feldspar is the same as K feldspar. Okay, because K is alkaline mineral element. Sorry, so therefore sometimes it's referred as alkali feldspars. Okay, so alkali feldspar or K feldspar, right? Potassium feldspar. It's termed as because it's a solid solution in between alkaline elements. It's a solid solution between alkaline elements, but this sodium rich end member, this one, sodium rich end member, where K feldspar and alkali feldspars are solid solutions. It's a common type of a end member because it has a solid solution in between calcium also, right? In this way, right? So you have a solid solution between sodium and calcium as well as sodium and potassium. So in most of the alkali feldspars, you don't see sodium usually, right? Because actually in nature, the occurrence of alkali feldspars in the nature contains very tiny amount of sodium. All the other cations are potassium. So that's why actually we call them potassium feldspars also, right? Since they do not contain sodium, very less sodium, very little amount of sodium is there if it accompanies. Otherwise, it's entirely potassium feldspar, right? So microcline and autoclase is two such varieties. And here you can see the microcline structure. It's more pinkish, right? Even sometimes you might have heard pink feldspar, right? Pink feldspar, granite or something like that, right? That means a granitic rock containing K feldspar, right? You can see some very tiny, some striations like linear feature, right? So that's a special texture which has the K feldspar has, right? So this is a microcline texture, okay? Or it's a twinning type, cross-hatch twinning type. In the thin section, you will see some cross-shaped pattern, right? Like this. It's a special texture. You can see this type of a special texture under the microscope, right? That's called microcline texture or cross-hatched twinning. Cross-hatched, H-A-T-H-E-D, hatched, cross-hatched, because it's a cross texture. In two directions, you have crosses like this. Okay, that's cross-hatched texture. So that is the Alkali Feldspar group, the solid solution between albite. AB means albite here, and here autoclase, right? Autoclase in this end, we call it autoclase. And the other solid solution series we call Plagioclase feldspars. Okay, Plagioclase feldspar series, which is a solid solution in between albite and nanotype. Albite and nanotype. You have solid solution, albite and nanotype. Okay, so albite means sodium rich feldspar, and nanotype is the calcium rich feldspar. Sodium rich and calcium rich feldspars. Okay, so under that group also you have a subcategories. You see here albite, that is the extreme end member of sodium, and then plagioclase, andesine, labradorite, and nanotype. Finally, bitonite and nanotype. Nanotype is the calcium-rich end member. So in between, you have this andesine, oligoclase, labradorite, bitonite compositions in between, right? Depending on the amounts of calcium and sodium available. So here it is the 50 mark. This is the 50 mark. So if anything is more than 50, that means if calcium is more than 50, that means towards this side, you can call any feldspar which is available in this group as Plagioclase Feldspar. Okay, sorry, anorthite composition, anorthitic feldspar, right? Of course, anorthite is just 100% calcium, but since calcium component is dominant above 50, you can consider it as an anorthitic feldspar, right? Not exactly the anorthite, but anorthitic composition. Usually, if it is greater than 90, the calcium component is greater than 90, then you can just straight away term it as anorthite. And for the other side is also the same way. You can see albitic feldspars, and if sodium component is greater than 90%, that means beyond here, then it's albite. You can call it albite. Otherwise, oligoclase and andesine, these are albitic feldspars. But anyway, all these ones are Plagioclase feldspars. All these ones are Plagioclase feldspars. So Plagioclase feldspars are also very very important to identify under the microscope. Also, you can identify actually. There you have some linear type of twinning variety, right? This we call polysynthetic twinning, right? So you will see this polysynthetic twinning in feldspars like this, right? The microcline you had is a cross-hatched twinning type, right? It's a two-way twinning. But in Plagioclase, you have polysynthetic twinning, right? Parallel layers like. So this is the composition of feldspars, and some images are there, microcline and albite, it's more whitish, and anorthite, Plagioclase feldspar, it's more it's in between whitish or some grayish appearance can be there, but not pinkish. Pinkish is always K feldspar, right? Microcline. Normal autoclase might look like this albite like color, right? Not pinkish, but when it is particularly microcline, you will see this very, very beautiful pinkish appearance. So otherwise, so slightly pink to whitish appearance can be found in any autoclase feldspar or alkali feldspar. Okay, Plagioclase never show this pinkish color, but they show white to grayish appearance. Okay, so it's just by color. It's not very easy to identify minerals, but this is a particular case. Okay. Right. Any questions regarding this group? Do you have any question? Right. So we'll move ahead. Then I can show you some alkali feldspar composition, but don't pay much attention to this phase diagram. This is a special diagram, how the composition and temperature varies, right? It's a little bit complicated until you learn about phase diagrams later on, right? But you should understand that this chemistry is very much controlled by temperature, right? So these phase diagrams are defined with the temperature and composition, TS diagrams, temperature composition diagrams. So anyway, so you can see under low temperature conditions, solid solution is unstable, as you know, right? So why is that? I said the solid solution is controlled by diffusion, and diffusion is controlled by temperature. So when you have higher temperature conditions, this diffusion is favored. You can easily see this diffusion changing compositions under solid state conditions. So in this feldspar, these alkali feldspars are solid solution between potassium and sodium, and Plagioclase feldspars are solid solution between sodium and calcium. So this solid solution behavior can be changed due to temperature conditions. But if the temperature drops, what happens? If the temperature drops all of a sudden, once these minerals were under solid solution conditions, making some composition, but when the temperature drops, it becomes unstable, right? It becomes unstable means the mineral changes its composition into previous or former compositions. It tends to turn into the former compositions. That means, for example, it's like you push a balloon and you remove it. You remove your hand, your fingers, right? When you push your balloon, you deform it, you change its shape. That means you are like changing the composition inside. But as soon as you remove your fingers, balloon turns into the original position quickly, right? But in the mineral also, if you change the physical control, that means physical parameter, temperature, it drops. If it drops, it tries to go back to its original composition, but during that time, the rock may be getting cooled or uplifted, or something is tectonically also happening into the rock. So that means this change doesn't occur continuously, right? This change does not occur continuously, so that you will see some patches inside the mineral where you see the solid solution composition. Also, in addition, the previous compositions also you can see as patches, right? So this particular feature we call exolution, right? So this particular feature is called exolution. So you have one composition in this part, right? Okay, let me. You have one composition in this part, whereas you have another composition in this part here. And we call this host, this part as the host, this whitish part as the host, and this blebs, or these small regions or areas where compositional change has happened with different composition. They are that is called exolution, exalt zones, right? Or exolution lamellae. We call them exolution lamellae, right? Because they are sort of lamellae. So if you increase the temperature again, what happens? These lamellae will disappear. These lamellae will disappear if you increase the temperature. But by that time, the rock may have come up to shallow levels where the temperature and both pressure are very low, relatively low. So nothing will continue. What is existing is arrested there. What is existing is sort of frozen there. So that's why you see this type of a feature. So you can see here exolutions. So this type of layers here, see different layers you can see. These are the exoled regions, right? The other things are zone twinning, right? Cross-hatch twinning. It is nothing to do with the chemistry there, but you can see some exolutions. So these are the exolution lamellae or blebs. Okay, here you have another example. Right, you have a host as well as you have these exoled parts. So this is what you call the exolution. So always remember, you can see this type of exolution in feldspars as well as pyroxenes. Commonly shown exolutions. Other minerals also possible if they are solid solution minerals. So solid solution minerals means they have a mix of compositions of cations, right? So that's why when they cool down or temperature drops, this exolution happens. So we call sudden cooling can take place and give rise to exolution features. Okay, temperature drop means cooling, right? It's a sudden cooling. So this is common in many solid solution minerals, but very particular in feldspars. and pyroxenes. Okay, so in alkali feldspar, this solid solution causes to form this albite and microcline in one grain, right? In a single mineral, you have now both zones. For example, here you have exolution bleb, and also you have a part of host, right? So that means two compositions are there in a single mineral. So these two compositions can be albite and microcline. Albite and microcline. Why is that? Because it is the solid solution. It is a solid solution. Albite and microcline or K-feldspar. That is the solid solution. Depending on the original composition of the mineral, whether sodium is dominant, potassium is dominant, or calcium is dominant, this solid solution can be taken place. Okay, so you see these phases are immiscible. That means they cannot mix each other. That's why you see them as separate blebs. Okay, so this happens, and this is a very common feature you can find in alkali feldspar. This is very common, and here you can see two zones, as I mentioned, that is albite and K-feldspar composition, right? So either microcline composition. Okay, albite or plagioclase can also be. That means if calcium was there originally, then calcium or the plagioclase composition can also be there. And if microcline was, potassium was there, then microcline composition is there. So we have a separate name for this type of a texture. If you see in a mineral, in a feldspar mineral, we call it perthite. We call it perthite. So if it is perthite texture, what you should have is, you must have the host here. Okay, I will draw again. So you have a mineral. This is host mineral, and inside that only you have these blebs, right? Inside this you have these blebs, right? So host is this mineral, right? Because it's the dominant area. So if you have this host as K-feldspar and these blebs as albite or plagioclase, then you refer this particular texture as perthite. Okay, then you refer this particular texture as perthite. And if it is opposite, that means if your host is albite, right? Previously your host was K-feldspar, right? This part is K-feldspar and this part is albite or plagioclase. Okay, then it's perthite. And if it is opposite, that means if you have the host here, the host is albite, and these blebs or these exolutions, if they are K-feldspars or microclines, then you call this antiperthite, right? That is the opposite. Perthite and antiperthite, that's the difference. Okay. So you can directly term that mineral as a perthite mineral or antiperthite mineral. Okay, those are the two different exolution behaviors you can find in feldspar: perthite and antiperthite. Albite and plagioclase exolution in microcline is called perthite, and K-feldspar lamellae or K-feldspar exolution in albite is called antiperthite, right? So the difference, you should understand what is host and what is blebs, what is the lamellae. Okay, so in addition, again you can have a special composition. Although this is not an exolution, I mean a real exolution is a slightly different from real exolution, but it's again an exolution. But we have a separate term for that. It's called myrmekite texture. It's a slightly different. There, what you have is quartz intergrowth inside the mineral, right? It's not a real exolution, but you can consider it as also a type of an exolution. Because there you see only the silicate composition there, because it's quartz, right? Sio2 only, no sodium, no potassium, no calcium, anything, right? So that's why some people are reluctant to term it as an exolution, but somehow it's a compositional change, forming some blebs or some lamellae. So, but if it is really feldspar, quartz inside the feldspar, host is feldspar, okay, and this exolution or these blebs are entirely formed of quartz, then it's called myrmekite texture, right? It's myrmekite texture, usually found in albite or plagioclase, right? Sometimes it's called intergrowth also, right? Because the quartz is growing inside that feldspar grain. That's the idea, right? So that's why people don't take it as an exolution, real exolution. It's a sort of a pseudo exolution type, right? So just to keep in mind, if you see that texture, that means in a feldspar, if you see this type of lamellae of quartz, then you can call it myrmekite texture, right? Found in feldspar grain. So these are the possible solid solution behaviors you can expect in feldspars. Understand? And also you can understand that this albite microcline, they have different stability regions in pressure temperature diagrams, but here it's a temperature composition diagram where you can see the potassium and sodium component amounts, the percentages, right? In terms of the temperature, how it changes, right? These are experimentally determined curves, experimental curves. So you will learn about these phase diagrams in your future years, future levels. Okay, right. Now we'll see some features of Plagioclase feldspar. There you can see twinning feature, polysynthetic twinning feature, right? Polysynthetic twinning, sometimes also called albite twinning. Here you see some parallel layers, alternative layers, right? That is twinning growth. So you see these minerals should be grown parallelly, right? So you have two minerals grown parallelly, like, so that is why this type of a texture is observed. Okay, and there is another type of twinning which we call oscillatory zoning. Actually it's not twinning, sorry, it's a zoning. It's a chemical zoning. Okay, it's different from twinning. Twinning is just a growth of mineral, right? Parallel growth of mineral like this. But this zoning means it's a compositional changes, right? The composition changes in between these ranges, right? So during the crystallization of this mineral, this feldspar, in igneous rocks, in magmas, if this feldspar is formed from a magma, during its course of growth, there can be some changes in composition like this. Okay, so these are zones, different zones of chemistries, different chemistries, zones of different chemistries. Okay, so this is what you call oscillatory zoning. If you see this type of beautiful zoning parallel to their crystal structure, right? You see, it's very, very beautiful structure parallel to its crystal structure phases. Okay, that is feldspar oscillatory zoning, right? So again, you should understand in feldspars there is no compositions in this region that is a miscibility gap, right? No feldspars occurring. So all the feldspars you can find are in this region. If you have a composition in this region, that is a K feldspar or K feldspar group, Alkali Feldspar group. And if you have a composition, all the feldspars will plot somewhere here. Like even you analyze any feldspar from anywhere in the world, in the planet, you will see this type of one. Other planets also, the compositions are like this, but no feldspars occurring in this region. That means there is no solid solution in between potassium and calcium. That's the point, right? There is no solid solution between potassium and calcium. because those two atoms, those two ions, when they formed into ionic structure, their ionic radii and valency, of course, valency for sodium and potassium, both valencies are same, but ionic radii is different. So when the ionic radii is different considerably, they cannot replace each other, right, in the crystalline structure. That's the reason. Okay. So this is Plagioclase Feldspar composition, and you can see some feldspars which are zoned here. Twinned here. This is twinning, polysynthetic twinning. But sometimes there are minerals, there are plagioclase which do not show this polysynthetic twinning, right? It's not essential, but it's a common feature, very common feature. Almost all plagioclase will show this feature. But there are situations which the mineral is tiny or it does not show sufficient areas of zoning. For example, if you see just only this part, you can't recognize whether it's K feldspar or plagioclase feldspar. And also here, when you see this type of a grain, it's very difficult to understand whether it's a plagioclase feldspar or autoclave feldspar. Right? Optically determining that is also very difficult, but there is a special technique called Mica-Levy method, right? Where we use the extinction angle to find whether it is albite or nanotype, right? In the practicals, we can see that method of doing that. So we will see how to distinguish that during the practicals, right? So there you see you change the optical, the orientation of the grain on the optical microscope stage, and there's a chart, Mica-Levy chart. That chart, you have the extinction angle one way and the composition the other way, and we can find out, depending on the extinction angle, what should be its composition. Okay, different depending on different angles, you have a curve there. Based on that curve, we can determine. Okay, we'll see that. But otherwise, basically, it's not easy to identify optically to distinguish whether it is autoclave or plagioclase. But you can do analysis like electron probe microanalysis, SCM or EPMA. Then you get the chemical composition. By that, you can easily recognize whether it is calcium bearing or potassium bearing or sodium bearing or whatever. Okay. Right. So here that chart is here. The maximum extinction angle is there, and the composition is there, whether it is albite, nanotype, or what. So depending on that, we can identify solid solution composition, right? Solid solution composition. So we use these zones to determine the extinction angle, right? So I think when you do practicals, you will understand how we can find the extinction angle. Extinction angle is angle where you see the mineral total black, like very dark appearance, and to that position, how many degrees you rotated the stage is called the extinction angle, right? In simple words. So for that, as a reference, you can use this zoning, these twinning lines, and if you rotate from this configuration to this configuration, this is the dark position, dark status, and when you see the bright maximum brightness again with these nice bands, then that is the angle, maximum extinction angle you can have for that particular mineral. Okay. So we can do that in a practical. Additionally, you have we have another type of technique. We call it staining technique. Staining. So what is staining? Staining means with the chemical, you try to see the color contrasts after applying it on the mineral, right? So if potassium feldspar is there, then it is shown in a different color. It will be appearing in a different color, right? Once you apply this chemical, right? So for staining, we use some cations, some chemicals, and then when you apply that chemical on top of your thin section, you will see two colors, right? For example, here you can see pink and yellow. So now you can easily distinguish what is pink, what is yellow, right? Like that. But other minerals like pyroxenes or quartz or anything, they don't show any bright colors with this chemical, right? So therefore, you can use particularly to identify plagioclase and K-phase. So for example, plagioclase is here very pinkish. I mean, it is not an optical color. Okay, after staining only, after applying the chemical, it turns into pinkish color. It's not any other property of plagioclase. Okay, don't get misunderstand. And K-feldspar becomes yellow. Okay, so then you can easily identify, okay, this is K-feldspar and this is plagioclase feldspar, like that, right? So this is how we can apply staining technique for a thin section to distinguish these two feldspar types. Okay, right. So this is about Feldspar group, and we covered now silica and Feldspar group, and then what we have is Feldspathoid group, right, under Tectosilicate. So Feldspathoid. What is Feldspathoids? We call them silicon poor, silica poor, as I mentioned. They don't have sufficient amount of silicon tetrahedra in their structure. So therefore, we call them silica undersaturated compositions. Silica undersaturated silicates. Although silicates, but the silica is undersaturated. It's not enough. Silicon amount is not enough. Usually you can find this in igneous rocks, and it's not very common also. We call them alkaline igneous rocks. There are such igneous rocks. You will learn details in your next years. So there you can see these feldspathoids. It's almost look like feldspar. Only chemically you can distinguish. Optically, it's very difficult to distinguish. So lucite, under the microscope, okay. So maybe in the hand specimen they show different colors like this. For example, lucite, nepheline, right? This is nepheline, and sodalite. You have the sodalite. It's a more bluish type. Okay. And yeah, different varieties can be there. And nepheline, more grayish, right? So you see nepheline here. So it's anyway, it's not easy to distinguish under the thin section, under the mineral scale, the microscope scale. Right. So these are the common feldspathoids: lucite, nepheline, and sodalite. Right. You just remember their names, but not necessary to remember the chemical formula. And we have one more thing, that is hydrous tectosilicate. So you can see the group again. Right. See some hydrous tectosilicates, water-bearing tectosilicates. See, and another sign, natrolite, heulandite, stilbite, right? They belong to zeolite group. They belong to zeolite group, whereas this belong to scapolite group. So I think you can, I will show you again the table: zeolite group, scapolite group, right? These are. Although they don't show any OH structure bonded into the their structure. That means it's not purely hydrous mineral, right? Remember, tectosilicates are anhydrous minerals. They don't have bonded OH component. So if you have a bonded OH component like in amphibole, then you can term it as a hydrous mineral. But since you don't have such, you can't term this as a hydrous mineral, although you have some adsorbed water molecule. So that's why I mentioned at the very beginning, adsorption is different than structurally bonding or absorption. Okay, because this H2O is just surface attachment. It can easily be removed. So you can't consider it as a hydrous mineral, therefore, right? Although people sometimes call hydrous tectosilicate, but this term is not perfect, right? In the literature, you might see this hydrous tectosilicate, but really it's not hydrous. It's just an attachment only to the layer. I mean, if you heat this one, this H2O can be removed. So once this H2O is removed, you will end up with the chemistry like this, for example, here. But still, this is a tectosilicate mineral. Okay. Although you remove this one. But in case of an amphibole or biotite, where structurally bonded OH is there, if you heat, that OH is going out as dehydration product. At the same time, the mineral also changes into anything else, some other mineral. Okay, so everything gets changed, but here it does not happen like that. So that's why we just consider it as a adsorbed water molecule, right? So you can't consider it as a real hydrous molecule attached into that. Okay. Right. So this is about the tectosilicates, where we have entirely covered the series. Okay, right. So if you have any question regarding this tectosilicates, please let me know now. We have now covered all the silicate types. I will give you detailed diagrams of these structural or site assignments, etc. in a separate handout, all the groups to be covered, right, under that special handout. Do you have a question? No questions? So you have to keep in mind that you must go through these lectures very carefully, because some parts may be a little bit complicated, but still they are understandable. So I will put all the recordings also, and also some additional reading materials. So you have to read some references as well. Although the university is closed, you can't go to the library, because in the library there are very important mineralogy books. So you must refer. Even after, whenever you come back physically to the university, you must go to the library and refer these mineralogy and optical mineralogy books, introductory books, right? There are introductory books. So you must read them. Otherwise, it's very difficult to get this knowledge. And also, as a geologist, if you want to work in the field as a geologist, this mineral knowledge is a must. Okay, that's why these courses have been made compulsory. Whatever the field you are going in the future, for example, hydrology, hydrogeology, engineering geology, whatever the field that you are going in your future career, you must have the mineralogy knowledge. Otherwise, you will be stuck in the middle, right? You will be having a lot of difficulties. And there are situations where For example, in the GSM, Geological Survey and Mines Bureau, some geologists were, they had to leave their job because their administration did not, their supervisors did not recommend them for confirmation in their job because of their lack of knowledge in minerals, right? They could not identify or understand different rock types simply, the mineralogy of rock types. That was a big problem some time ago. So therefore, you have to learn these minerals and all this structural geology, minerals, mineralogy, optical mineralogy, and these compulsory modules very, very carefully throughout the 4 years. Although we teach this at the second year, introductory levels, you have to apply that at your 400 level as well, 300 or 400 level as well, right? You will not get chance to learn it again, but this knowledge you have to apply. So that means you must digest it very well, and otherwise you can't do like just following course modules. So you do one course module and get the grade and forget it in the next semester, right? You can't do like that, right? This must be carried forward throughout, right? Otherwise you can't compete the engineers also. If, for example, for those who want to go for engineering geology, you will have to work with engineers, right? Engineers will know whatever you learn under engineering geology. Engineering geological principles, they have some understanding, and also they can learn if they want to work hard. But what they can't learn and what they don't know is mineralogy, right? But if you don't understand the mineralogy, you can't compete the civil engineers in the field, right? Because they will just easily compete with you in terms of other engineering principles, right? So foundation design or whatever, road design or road constructions, whatever, they can learn geological aspects easily with in terms of engineering geological principles, shear stress, direct shear, all these applications, they are very familiar, right? But describing a rock in terms of mineralogy is also very important when you select foundation. And for example, dam sites, if you want to construct dam sites, you have to select correct rocks, and consequences you have to understand what will happen in during weathering or during oxidation or reducing conditions, which can be available after filling of the reservoir. For example, Samanala, what has happened now? There is a rapid rock weathering in the dam site, right? So that will make some leakages in the future, right? There are huge rock weathering is happening. That is due to sulfide bearing mineralogies are there. So engineers don't understand that one. They just are puzzled why this is happening. They can't explain it, but you are the only people who can explain that and suggest remedies for that. So therefore, this mineralogy knowledge, optical and other descriptive and all the other general types of mineralogical knowledge that you learn from your first years is a must, right? Otherwise you will have a very dangerous future. Remember that. Okay. All right. Now I will share with you some other aspect which is also very important. Right now, I think you can see my new file. There we will discuss about the solid solutions and some related aspects in detail. Okay, so some basic knowledge also I have to remember. I think the chemical formulas. So you know that subscripts in a chemical formula represent the relative numbers of elements present, right? For example, Sio2. So here Si1, although we don't show one there, O2, that means 2 atoms are there, oxygen 2 atoms are there with 1 silicon atom, likewise. So that is the relative numbers of elements present there. Okay. It can be multiples also, right? You can reduce the formula considering if it is divisible, so you can do like that. So SiO2, you can make it as Si2O4 like that. That is also possible, right? And parentheses separate complexes or substituted elements. So, you know, if you have something like here, if you have something like here, sorry, you have substituted component, right? That means you have substituted component with two atoms, two ions, ionic compounds. That means ion is bonded to three separate OH. That indicates, okay, like that. So similarly, olivine. So you know the chemistry of olivine now already. Here you see, in other words, you can represent it also, iron and magnesium solid solution. That means 0 to 100%. Whatever the number, we don't know, you have to analyze and see, right? It can be 0 to 100% magnesium and 0 to 100% iron. Of course, you know, if it is 100%, the other element should not be there, right? If 100% magnesium, then there will be no iron. If 100% iron, there will be no magnesium. That is obvious. But it indicates in a solid solution mineral, this replacement can be there, okay? And then, you know, the stoichiometry in chemistry also, you have learned about this stoichiometry. So how many elements combine with the other one, that is determined by the stoichiometry of the molecule, and you can give a formula for the molecule based on the stoichiometry as well, right? And solid solution, so what is happening is, as I showed you before, the replacement is happening, but you can't damage the stoichiometry there, right? You can't damage the stoichiometry. That's why this valency and ionic radius is important, whether to decide whether you can substitute that particular element or not, right? So for example, in feldspars, I said calcium cannot be replaced by potassium, right? But sodium can be, right? So likewise, you have to decide the stoichiometry. I mean, it's naturally controlled by the stoichiometry. So we term N members, as I said, it's a species which contain 100% of one of the elements, right? So it's a N member. So for example, we had albite and nanotype. Those are the N members, 100% one particular element, okay? Right. So then we have the compositional diagrams. So what are the compositional diagrams? Just a kind of a sketch which shows the composition, possible compositions, right? It's not actually a sketch. You can draw a sketch, but it should be drawn into a scale, right? If you want to really represent their chemistries, you have to draw it into a scale, right? So it can be, if it is just two N members, right? For example, here one N member, the other one is this one. So what is this N member, two N members? Phthalate and phosphorite. So what are those things? Phthalate and phosphorite, they are olivine N members. Okay, iron and magnesium N members of olivine. So that is linear. So you don't have any other third element there to replace. So therefore it's linear. But in some cases, you may have three elements. You have three elements. For example, here iron, magnesium, and silicon. But you know, silicon is not coming to a solid solution for the phosphorite or phthalate. Therefore, you don't need to show it in a triangular diagram, but just to show you that if you want to add another element, it becomes a triangle. Only you have shown this one, right? But here you have the phthalate, enstatite, ferrocylite. It's not phosphorite, right? So it's wrong. It's here. I mean, this is just a sort of what you call it, an example only for showing the solid solution, right? Olivine solid solution, you know clearly it's phthalate and phosphoride, it's linear, right? But pyroxene solid solution is triangular, right? Why? You have iron, magnesium, and calcium, not silicon, right? It should be calcium. But in orthopyroxene, as we learned, calcium component is very, very low. Okay, calcium component is very, very low. So that's why you have actually enstatite ferrosilicate also put into this formula. Sorry, in this triangle, right? There is no calcium. Silicon is common for both. I mean, olivine also has a silicon, but you don't need to consider silicon because it is not a part of solid solution. Usually, in order to present the diagrams, compositional diagrams, what we do is only we take the solid solution elements into that. Okay, so that's why we don't need other elements like aluminium, silicon. We don't need to put into the composition diagram. Although you have, you can put it as a compositional diagram also, right? Into a composition diagram, you can put silicon or aluminium also because you know the chemistry of that. You know, you can analyze it and determine the composition. So then you can plot in between. But remember, solid solution will not take place in between those. Only solid solution possible elements we take into the compositional diagrams, showing compositional diagrams. All right. So olivine is a linear solid solution. You can represent in a line, linear, in a linear way, and orthopyroxene also you can put in a linear way because the amount of calcium is very, very limited, right? Almost nothing, right? So therefore, you can just take that part only and represent in a line. That is okay. But clinopyroxene, you can't do that because calcium is there in addition to iron and magnesium. So it's better if you take a triangle and show both orthopyroxene and clinopyroxene together. That's the easy way. Right. For mica, also you have different compositions. For mica, also you have different compositions. Solid solution compositions and phlogopite, lepidolite, and muscovite. Phlogopite, lepidolite, and muscovite, you have those compositions as well. Okay, right. So that is the solid solution behavior. Okay, right. I can see some people are sleeping. Okay, so you want me to stop the lecture? So when you are sleeping, you don't know your body parts are moving. Automatically, your video is getting on. I can see windows, roofs, and beds and everything, right? You are not supposed to do like that. You have to be attentive to the lecture. If you can't, you can just leave. If you don't want to continue. People are doing hard for your future. If you don't take that into serious, you can leave. There is no need. Okay, so if you get to the amphibole, what is the composition there? You can have a solid solution. Oh, sorry. Yes, for representing the solid solution, you can take a triangle or diagram representing the solid solution, whatever available. Okay, right. So we have seen these compositions and all composition, and also remember this hornblende composition is very, very complicated. Okay, so there is possibility for solid solution between different phases. There are several elements, different elements you can have. Their solid solution can be possible in between those. So anyway, autoclave composition, we considered the autoclave composition from sodium to calcium. That is plagioclase composition, and autoclave composition we considered from sodium to potassium side. But you know, Autoclave Feldspar is very particular, having potassium-rich end member, right? Then the microcline and K feldspars, autoclaves, they are very rich in potassium composition, and it seems almost nothing with sodium. But if you analyze naturally, there will be at least a little amount of sodium there. So therefore, we consider still sodium potassium solid solution is possible, but not in this site. Calcium potassium is not happening. So sodium calcium is there, sodium potassium is there as a solid solution. Right? No feldspars in this region. That is completely miscibility gap. Okay, so you have the miscibility gap very clearly. And then we have the Garnet group, where the solid solution composition, almandite, spessartine, and pyrope. We call it Feldspar series. Feldspar series means magnesium, manganese, and iron solid solution group, right? For example, pyrope, almandine, spessartine. These ones, almandine or almandite, both is possible, okay? Right, remember, almandine is a common form. So we call this as Feldspar because PY is here, AL is there, and spessartine, this part. So Feldspar, it's a brief form to remember. Pyrope, almandine, and spessartine. And the other group, it's ugranite. We call ugranite. This is a calcium part. So aurovite, grossular, and andrite. Aurovite here, grossular, and andrite. Those compositions, right? Ugranite. It's called ugranite, just for remembering purpose. So remember, this solid solution can take place very complicatedly in garnet, right? So these are isomorphous mineral with the solid solution happening. Okay, right. So you have the wollastonite. You have the wollastonite in pyroxene series. So you can remember wollastonite is not a real pyroxene. It's a pyroxenoid, right? Remember? Right. So that's why we have a miscibility gap here, saying that no real pyroxene minerals. Only wollastonite is there, but still it is kind of a deformed. It's a distorted structure, right? Remember? So you have to go back to your lecture notes, previous lectures, and remember whatever you are not recalling now. So we call therefore this as the Pyroxene Quadrilateral. Actually, this is not real triangle because we are not considering pyroxene from here onwards. Okay. So therefore, you can consider it as a Pyroxene Quadrilateral because we are not taking much care to this part. Okay, right. Okay, so this part is quadrilateral, pyroxene quadrilateral. You have the clinopyroxene here. This part you have the clinopyroxene and orthopyroxene, this part. So that's why I asked you that you can represent this orthopyroxene in a linear way also, right? Because you have a very little range there, right? Not beyond there. Okay. So this compositional variation in minerals is determined mainly by what? Is mainly by the solid solution. So you have the solid solution here. So what is happening for solid solution? You must remember this solid solution as the exchanging composition. So therefore, these minerals you can consider as not necessarily fixed composition. Although we define the mineral as a fixed chemical composition, it's not necessarily fixed, but it has a definite composition. You know, it's having iron and magnesium, but it's not fixed. Okay, that's the difference. I think I explained this at the very beginning. by definition, minerals should be having a definite chemical composition. But this definite composition does not mean that iron and magnesium ratio can be changed. Right? The ratio can be changed, but it's still iron and magnesium, so it is definite. Okay, but it's not fixed. So that is important to understand. Okay, so solid solutions occur as a result of ionic substitution. As a result of ionic substitution, this solid solution happens. And the size of the ions is a matter for this one. And also the charges of the ion is also important, right? Then what is important is temperature, right? Pressure also matters, but temperature is the main determining factor for this substitution to take place. So this is very, very important. So great amounts of substitution take place under high temperature conditions. Okay. So we have different types of solid solutions. In rocks you can find, in minerals: substitutional, interstitial, and omission. Right? These are three types. We'll see what these three types are. We'll see what these types are. Right? Substitution solid solution is the simple substitution. That is just like iron magnesium substitution, something like that. So this can be completely solid solution completed or partial or limited sometimes. That means some solid solution does not happen completely. It depends on the sizes of atom and mainly the size of the atom. Okay. So the solid solution series to be complete is said to be when the sizes of ions are same, nearly the same sizes of atoms are there. I mean ions, sizes of ions, cations. If the substituting ions of elements are same, then complete substitution can take place. Otherwise, if different size ions are there, they can fit into the structure in some way by deforming the crystal lattice, right? Because it's like if somebody is very fat, wants to sit in between two thin people, right? You have to be very squeezed, right? Like that. So you get deformed. Likewise, the crystal becomes deformed, but still the substitution can take place to some extent. That is partial substitution. Okay. So usually you have this substitution, as I mentioned, iron and magnesium substitution. In olivine, for example, you have iron and magnesium substitution. And where else? You have pyroxene, biotite, hornblende, right? This substitution is common. Complete substitution is happening because almost equal ionic substitution is happening in between these elements. And then it's possible iron and manganese substitution, right? You see ionic radii is also given. So you have, for example, here iron and magnesium, ionic radii is almost same, very close, right? Therefore, complete substitution is possible. In manganese also it's not very far, it's close. So therefore, complete substitution can take place, but some limited amount only, because manganese is not available in abundant quantities in rocks, unlike iron and magnesium, right? Manganese is available in limited quantities. So therefore, sometimes the solid solution is partial, right? Some examples are siderite, iron carbonate, and rhodochrosite, manganese carbonate. So these two can be solid solution, behave in the solid solution behavior. Iron and manganese, right? Those are carbonates. Again, you have manganese and iron, sorry, magnesium, previously we had iron and manganese, and now we have magnesium and manganese. So again, the composition is, solid solution is possible, not impossible, but you see the sizes are a little bit different than the previous case. So therefore, if solid solution to happen, it should be partial. But usually you don't see such common examples, but still in siderite rhodochrosite also, this manganese substitution can also be there very rarely. So therefore, you can take the same examples here also. But definitely partial solid solution is there. Okay, right. And then what you have is sodium and potassium solid solution. You can see the valency is also same, and ionic radii is not very different. So therefore, complete solid solution can be happening, right? Alkali Feldspars. And ferric and aluminium, although the valency is equal, ionic radii is a little bit different in between. Okay, so therefore you can have a limited solid solution. For example, in Alkali Feldspar, right? In place of aluminium, you can have ferric, right? It's not the albite and nanotype type of solid solution. This is a very rare type of solid solution. That's why I told you in a previous diagram, where was it here? Yes. Sometimes you can consider non-solid solution, I mean not common phases as well, elements as well. Silicon or aluminium is possible, right? Iron and silicon solid solution is possible, but very rarely it happens. Okay, right. Now what you have here, bromide is here, chloride is here. So those are halogens, right? These halogens can have complete solid solution. Why? The ionic radii is almost same, right? Not very much different. So complete solution. So KCl, KBr is possible. KCl, KBr is possible. So you I think you can remember now when I tell KCl. These days there is a hot debate on KCl, right? Organic versus and inorganic. The fertilizer, KCl, potassium chloride. What is potassium chloride? KCl is silvite. It's a mineral, right? It's a mineral, silvite. You know silvite? It's KCl, potassium chloride, silvite. So remember the definition of mineral. What is the definition of mineral? It contains an inorganic part, right? Mineral is an chemical substance which is inorganic, having a definite chemical composition, naturally occurring, like that, right? So how come KCl then, right? So you have a point to think about. Okay, so this is a natural mineral, right? It's an inorganic product, right? And KBr can also be there, potassium bromide, right? And OH fluorine substitution can be there, anionic substitution, both cases. And you see the ionic radii is very close. Therefore, complete solid solution can be there. In biotite, you can find this one. In biotite, you can find this one. In place of OH, you can have halogen, right? So I think I explained it before in the last week. Okay. Right. So this is complete or partial substitution, and there is one important fact, not a solid solution type. Okay, under substitution solid solution, you have another important point, right? Under this one, right? Substitution. There we consider something called coupled substitution. Coupled substitution. What is coupled substitution? Couple means two. Okay, so this results in having to make another substitution in order to maintain the charge balance. So usual substitution take place, say iron and magnesium, right? Both are divalent, right? Iron and magnesium both are divalent. So in that case, there is no charge imbalance. But in places where sodium replaces with, say, iron, if possible, right? So then valency change is there, right? Sodium is +1, iron, ferrous is +2, right? So then you have charge imbalance. To compensate that charge imbalance, there should be another substitution taking place. So that is why we call it coupled substitution. Two substitutions are taking place at the same time, right? So this is very common in places where like silicate minerals, where aluminum is there, which substitutes for silicon, because it's +4. Usually this happens in silicates. Aluminum and silicon get substituted. Then +1 charge is excess there, or deficiency or excess charge can happen depending on the nature of the substitution. So there, another substitution should take place naturally to balance the charge imbalance or the compensate the charge imbalance. So that is what you call coupled substitution. So for example, Plagioclase, normally sodium and potassium replaces, right? At the same time, silicon and aluminum replaces. So here you have +1 difference, and therefore this sodium substitution is easy for that structure. Otherwise, sodium substitution is not very easy for calcium places. So that's why it have actually speaking, first what to happen is silicon and aluminum substitution. Then to compensate that charge, sodium substitutes. So that is what happening in Plagioclase. Okay, that the steps are different. Although we just consider that sodium and calcium replaces each other, it's happening because of a coupled substitution. Okay. Right, now Plagioclase, that's why you have this type of a complete substitution with the coupled substitution. And also you have pyroxenes. In pyroxenes, again, you have this calcium, magnesium, and sodium, aluminum. Usually what is happening is these two substitutions are taking place and four cations are produced there, right? So therefore, you have this diopside composition like this, and Zeolite composition. Sodic pyroxenes, remember, that's how the sodium has come into the pyroxene structure. Otherwise, usually in pyroxene, you don't have sodium, right? Calcium, magnesium, or iron is there. So those are divalent. So easily substitution can take place. But places where high pressure conditions are prevailing, sodium can be there coming into the structure. That's why I told you that sodic pyroxenes are there, right? So that is a coupled substitution, but it's a limited substitution, remember, because it happens only under high pressure conditions, right? Then what you have is extensive substitution is taking place with aluminum, iron, and magnesium, titanium, right? Actually, what is happening is magnesium ion substitution is taking place as a result of aluminum and titanium substitution. So that first happens, and then magnesium ion substitution is taken place. That is extensive substitution, very, very extensive. In spinel, right? In spinel, you have this substitution. So spinel is not a silicate mineral. So that's why we did not learn it under silicates. Spinel is an oxide, right? Alumina, corundum, ruby, sapphire, right? All those are oxides, right? So you should understand other mineral groups are also there, right? So in your first year, you learned about the systematic classification of minerals: silicates, oxides, hydroxides, halides, likewise, right? They don't belong to silicate, right? So that's why we did not consider. But now it's time for you to read and get or refreshed your first year knowledge also in terms of other types of minerals. So remember, you have to learn about read about oxides, hydroxides, like halides, like minerals also. For example, malachite, they are hydroxides, right? Likewise. And sulfides, there are many types of groups, subgroups, groups and subgroups, right? We don't have time to do everything. So as extra reading, so please go through about these other groups, minor groups. But oxide is not a real minor group. It's extensively applied because spinel, alumina or corundum, you have such types of minerals there in commonly found in rocks, right? So you read separately on them. Okay, right. So this is about the solid solution, and this is a substitutional solid solution. And then interstitial solid solution means in some crystals, what is happening? Some sites are there, some crystallographic sites are there, some places, locations are there. They are not normally occupied by ions. So these are considered voids, some blank spaces. So these blank spaces can be occupied by some other cation. So that is called interstitial solid solution. Okay, so those are interstitial solid solutions, which is not happening very frequently. Okay, which is not happening very frequently. And then what you have is omission solid solution, omission solid solution, which is happening when higher charge of cation substitutes for an lower charge cation. For example, trivalent cation substitutes to divalent or monovalent cation, right? So in order to maintain charge balance, as I mentioned in the previous case, as a couple substitution, another lower charge cation should have take place. So that means again the coupled substitution is taking place under omission solid solution also, right? For example, in microcline, in Feldspar, lead can replace potassium, 2 potassium ions. So that is how it happens. That is how it happens. Okay, one site is left vacant in that case. So like this, these are the solid solution types. So I will upload some of these extra reading materials into the Google Classroom so that you can go through more details also, right? And do the assignment also. We will end our descriptive mineralogy lecture series here. But in case if you need any discussion, please let me know so that we can arrange extra discussion class as well, right? So 2017 group still, if they need some discussion, please let me know. But anyway, you are coming to the university from after 13th November. So we can arrange some physical classes as well during the examinations, after examinations and practical sessions if necessary, right? So, but you have to inform us the respective courses, which course you need some extra class like that, right? You can send me an email or whatever communication in the Google Classroom. Also, you can put a message. You can leave a comment there, right? So anybody can are free to leave comments there, so that we can get your feedback and do the needful for you. Okay. Okay. So now I will stop here. So I hope you will do the lectures. I mean, you will read more additional details and do in your at your best in your exams. Okay. Yeah, somebody is saying that about the recordings. I think I have already shared the recordings to the 2017 batch as well. I have given you the link, so you can go through for these recordings. Anyway, I will share again. I will share again the link for the recordings for the 2017 batch as well. Yeah, I think already I sent to the 2017 batch also, right? Since your Google Classroom is archived, you don't see anything there. The materials, I think you can't download or anything, but by email I circulated all the links. So anyway, I will do that again, so you can refer. Okay, thank you, and I will stop here now.